June 17th, 2013, 7:45 in the morning. A 7-meter wave slams into the bow of a massive container ship in the Indian Ocean. The crew feels a violent shudder ripple through the deck beneath their feet, followed by a sound that shouldn't exist on a modern vessel. A thunderous crack echoing through the steel hull. The MOL Comfort, a state-of-the-art container ship only 5 years old, carrying 4,293 containers worth hundreds of millions of dollars, is tearing itself apart. 26 crew members, 200 miles from the nearest coast, are about to witness something that will change container shipping forever. This ship wasn't built with ordinary steel. It was constructed with ultra-high tensile steel, a revolutionary material that promised superior strength and lighter weight, the future of shipbuilding. But what investigators discovered in the wreckage would expose a terrifying flaw in modern maritime engineering. How does a nearly new ship with cutting-edge materials just snap in half in manageable seas? The answer is more disturbing than anyone imagined. In 2008, Mitsubishi Heavy Industries, one of the most respected engineering companies in the world, completes construction of a post-Panamax container ship called APL Russia. Post-Panamax means the vessel is so massive it can't fit through the Panama Canal. This ship represents the cutting edge of maritime technology. She measures 316 meters long and 45 meters wide, with capacity for 8,110 containers. But the most revolutionary feature isn't her size, it's what she's made of. Ultra-high tensile steel. This advanced material has superior strength compared to ordinary steel, allowing engineers to use thinner metal plates while maintaining the same structural integrity. The result? A lighter ship that can carry more cargo while burning less fuel. It's a shipbuilder's dream. APL Russia's sister ship, built in 2007, was one of the first vessels to use this steel in construction. The industry watched closely. If this worked, it would transform how we build ships. The vessel is powered by a massive 2-stroke diesel engine, a simplified design with fewer moving parts that produces enormous power and runs reliably for months at sea. She uses a single fixed-pitch propeller, the simplest and most dependable propulsion system in the industry. Everything about this ship is designed for efficiency and reliability. Class NK, Japan's leading ship classification society, conducts rigorous inspections during construction. They certify that APL Russia meets every international safety and design standard. She's approved for global service. In June 2012, APL Russia is chartered to Mitsui O.S.K. Lines, one of Japan's premier shipping companies, and renamed MOL Comfort. She joins an elite fleet servicing critical trade routes between Asia, the Middle East, and Europe. But as container ships grew larger and larger through the 2000s, engineers began noticing a troubling pattern. These massive vessels experience structural stresses that smaller ships never encountered. The sheer weight of thousands of containers, combined with the forces of ocean waves, created flexing and bending that pushed hulls to their limits. In May 2013, just 1 month before disaster strikes, Class NK conducts MOL Comfort's mandatory 5-year special survey. Inspectors examine every critical system. They check the hull for cracks, corrosion, and deformations, focusing on high-stress areas like the midsection, where hogging and sagging forces are strongest. Hogging occurs when the middle of the ship rises on a wave crest, while the bow and stern hang unsupported, creating upward bending stress. Sagging is the opposite, when bow and stern ride wave crests and the middle sags downward. These forces are constant and relentless. The inspectors test the main engines, auxiliary systems, and propulsion. They examine ballast pumps, fuel tanks, and cargo handling gear. They verify that bulkheads, watertight doors, and hatches can withstand flooding. They inspect lifeboats, firefighting equipment, and navigation systems. After weeks of detailed examination, Class NK reaches their conclusion. No major issues found. MOL Comfort is certified safe for another 5 years of service. June 2013. MOL Comfort prepares to depart Singapore on a westbound journey toward Jeddah, Saudi Arabia, a critical route connecting Asian manufacturing to Middle Eastern and European markets. Before any ship can leave port, the crew must conduct pre-departure stability calculations to ensure the vessel is safe to sail. They calculate total weight, making sure it stays within the ship's load line limits. They account for cargo weight, ballast water, fuel oil, and fresh water. They measure the center of gravity to ensure stability. They check the draft, the depth of the ship sitting in the water, at 3 points. Forward draft measures 13.45 meters. Midship draft is 12.9 meters. Aft draft reads 14.6 meters below the waterline. These numbers tell a story. The ship is already hogging slightly, with the midsection sitting higher than the bow and stern. It's within acceptable parameters, but it's there. The vessel carries 2,287 tons of heavy fuel oil, 490 tons of low-sulfur fuel, 139 tons of gas oil, and 6,160 tons of ballast water, all carefully calculated to maintain proper trim and stability during the voyage. The cargo manifest shows 4,382 physical containers loaded on board, equivalent to 7,041 TEUs, the industry standard measurement of 20-foot equivalent units. The cargo is distributed across the deck and holds to minimize stress on the hull. Everything is balanced. Everything checks out. The crew of 26, comprising experienced seafarers from the Philippines, Russia, and Ukraine, board the vessel. The master, chief officer, and chief engineer review the voyage plan. Their route will take them across the Indian Ocean, through the Arabian Sea, and eventually through the Suez Canal toward Europe. The ship's weather routing software provides forecasts. Strong monsoon winds expected, moderate to heavy seas in the Arabian Sea. The crew notes the information but isn't alarmed. MOL Comfort is a modern vessel built to handle rough conditions. On June 11, 2013, MOL Comfort departs Singapore. Everything is by the book. Every calculation is correct. Every system is functioning. The ship is certified safe. But hidden within the ultra-high tensile steel hull, microscopic cracks are already forming, invisible fractures that will soon become catastrophic failures. The ship maintains a steady speed of 18 knots, with the engine running at 83 revolutions per minute. For the first few days, the voyage is routine. The crew settles into their watch schedules. The chief officer monitors cargo and container lashings. The chief engineer keeps watch over the machinery systems. Everything operates smoothly. But on June 16th, 5 days into the journey, conditions begin to change. The wind picks up, reaching 38 knots. That's strong enough to create steep, punishing waves that challenge even the largest vessels. The swell builds to 6 and 7 meters, rolling across the ocean and slamming into MOL Comfort's bow at regular intervals. The bridge crew responds according to standard procedure. They reduce the engine speed to 79 revolutions per minute. The ship's average speed drops from 25 knots down to 17 knots. This will put them slightly behind schedule for their arrival in Jeddah, but the master prioritizes safety over speed. The weather routing system updates with new guidance. warning of increasing swell heights along their path. Monsoon season in the Arabian Sea can be treacherous, but the officers on watch don't consider the situation alarming. MOL Comfort is a modern ship. Her pre-departure stability calculations showed no cause for concern. She's designed to handle conditions far worse than this. The chief officer wakes the master, and they meet on the bridge to discuss the conditions. After reviewing the weather data and observing the ship's motion, they decide to alter course slightly. By approaching the swell at a different angle, a longer section of the hull will contact each wave, which should create a smoother ride and reduce stress. The engineers below deck report that everything is operating within normal parameters. They'll continue monitoring closely. At 0700, the carpenter performs his daily soundings again. His readings are identical to the previous day. All the tanks are holding steady, but as he moves through the ship, he notices something odd. The forward end seems to react to the waves differently than the aft end. The timing feels wrong, like the two halves of the ship aren't quite synchronized. He reports his observations to the chief officer. They review all the calculations together. Everything checks out. All the measurements are within acceptable ranges. There's no obvious sign of structural problems. It's not considered urgent, and they decide to continue monitoring. But here's the question that haunts maritime disasters. What do you look for when everything on your checklist says everything is fine? What they can't see, what the chief officer and the carpenter can only sense through years of experience at sea, is that the ship's steel hull has been stretched beyond its design limits. After only 5 years of service, tiny fractures, completely invisible to the naked eye, have developed in the ultra-high tensile steel plates. These microscopic cracks are growing with every wave that hits the bow, spreading through the metal like a spider web. At 0745, MOL Comfort is almost 200 nautical miles off the coast of Yemen. A set of waves, each reaching 7 meters high, slams against the port bow. The force of the water reverberates through the steel hull, and the crew feels something they've never experienced before: a sharp, jarring snap. Unlike the normal creaking and groaning of a ship at sea, this is different. This is wrong. On the bridge, the chief officer and the lookout immediately sense that something catastrophic is happening. The lookout stares forward and sees something impossible. The forward end of the ship looks misaligned. For a moment, he thinks it must be an optical illusion caused by the waves and spray. Ships don't just bend in the middle. This is something you see in maritime disaster investigations. There's often a disconnect between what's actually happening and the crew's ability to recognize that a disaster is unfolding right in front of them. The human brain resists accepting the impossible. The chief officer calls the master to the bridge immediately. Below deck, the chief engineer is stationed in the machinery control room when he feels the impact. Moments later, alarms start sounding throughout the ship. The pipe duct keel space, which runs along the bottom of the vessel, is flooding. Water is pouring into cargo hold number 6. The portside fuel tanks have been breached. The chief officer reaches cargo hold number 6 and finds it already flooded to the height of 1 container level. He examines the side shell plating, the outer wall of the hull, and sees cracks running along the seams. But these aren't small stress cracks. These are gaping breaches, and they're widening with every wave that hits the ship. He pulls out his phone and takes photographs, then rushes back to the bridge. When he shows the master the images, both men understand instantly. MOL Comfort isn't just taking on water, she's breaking apart. The master immediately orders the main engine speed reduced to 45 revolutions per minute. He needs to take pressure off the failing hull, but he can't stop the engines entirely. If the ship loses all forward momentum, she'll drift parallel to the waves, which could cause her to capsize in these rough seas. He must keep the vessel moving to maintain stability while they assess their options. The helmsman adjusts the heading to approach the waves at a slight angle, minimizing direct impact. But water continues flooding the affected areas. Hold 6 is filling rapidly. Oil traces begin appearing in water discharge from the pumps, indicating that fuel tanks have ruptured. By 0830, the cracks in the hull have widened dramatically. The midsection of the ship is visibly sagging under the combined weight of the cargo and the relentless force of the waves. On the bridge, the crew watches in horror as the ship's motion becomes increasingly erratic. The bow rises sharply, completely out of sync with the momentum of the stern. It's as if the two halves of the ship are no longer connected. Containers begin toppling from the deck, crashing into the sea. At 0900, the master makes the decision. There's nothing more they can do. He sends out a distress signal. "This is MOL Comfort. We are breaking in two. Request immediate assistance." The message goes out across all emergency frequencies. 24 nautical miles away, the container ship MV Yantian Express picks up the distress call and immediately alters course to assist. On board MOL Comfort, the crew musters at their designated abandoned ship stations. They don life jackets with practiced efficiency. As the crew prepares the lifeboats, the chief officer makes one final inspection run through the underdeck passage. What he sees will stay with him for the rest of his life. The cracks in the hull are no longer just structural deformations. They are gaping breaches, and daylight is streaming through the sides of the ship. The vessel is literally tearing itself in half. At 0945, the master issues the final order: abandon ship. All 26 crew members gather on the starboard side and board the enclosed lifeboat. Timing is critical. If they launch at the wrong moment, the lifeboat could be crushed against containers floating in the heavy seas. They wait for the right moment, and the lifeboat is successfully released. It motors away from the stricken vessel as the crew watches their ship die. The MV Yantian Express approaches rapidly. By 11:36, all 26 crew members are safely rescued and brought aboard. They're exhausted, traumatized, but alive. 12 minutes later, at 11:48, MOL Comfort reaches her breaking point. With a sound like thunder, the ship fractures completely into two sections. The bow and stern drift apart, floating independently on the Indian Ocean swells. A state-of-the-art container ship, only 5 years old, built with revolutionary materials and certified safe just 1 month earlier, has snapped in half like a toy. Salvage teams mobilize immediately, but the situation deteriorates fast. On June 18th, they secure the bow section with tow lines, hoping to save it. The stern section is already tilting dangerously. 9 days later, on June 27th, the stern sinks in 4,000 meters of water, taking 1,700 containers and 1,500 tons of fuel oil down with it. An oil slick spreads for miles. Then, on July 6th, fire breaks out on the bow section. The blaze rages for 4 days, fed by cargo and fuel. On July 10th, the bow section sinks 160 nautical miles off the Indian coast, carrying another 2,400 containers into 3,000 meters of water. MOL Comfort is gone, both halves resting on the ocean floor. The insurance claims reach $400 million, one of the largest maritime cargo losses in history. Over 100 lawsuits are filed against Mitsubishi Heavy Industries, alleging design flaws. The International Association of Classification Societies responds with dramatically stricter rules. Ultra-high tensile steel now requires ultrasonic examination to detect stress fractures. Real-time hull monitoring systems become mandatory on large vessels. Advanced cargo distribution software prevents excessive stress on weak points. MOL Comfort changed how we build and inspect every container ship sailing today. If this story opened your eyes to the hidden dangers in modern technology, hit that subscribe button and turn on notifications. Drop a comment and tell me, are we pushing ships too far for efficiency? Thanks for watching. Stay curious.